Hi, I am Farhan Fawad Abir. As a part of the first assignment of CAP 5610 Machine Learning course, I am presenting this paper, Speaker-Follower Models for Vision and Language Navigation. This paper was published in NeurIPS 2018 and as of today, it has 349 citations. Now let's take a look at the Vision and Language Navigation task. Vision and Language Navigation, or in short VLN, is the task of navigating through a real-world environment based on natural language instructions by an agent, or it can be a robot. The term VLN was first introduced by Peter Anderson and his team in their paper in 2018. Actions performed by an agent based on natural language instructions was already in study at that time. However, the problem did not have any structured approach before their work. Here at the right, you can see an instance of VLN task taken where the agent needs to take action in real-world indoor environment using computer vision and natural language understanding. So let's take a look at the problem definition of this work. The authors of this paper identified three fundamental problems and provided some intriguing solutions. Firstly, they introduced a data augmentation technique. They call it the speaker-driven data augmentation, which actually solved the data annotation problem which existed at that time and also exists right now in 2023. So their room-to-room dataset was not actually large enough to accommodate both computer vision and the NLP model training. So that's why this process actually improved the performance of the overall model. Secondly, they introduced a pragmatic reasoning, which is in layman's term a post-processing technique to resolve the ambiguous references provided by the base model. And thirdly, they, prior works used low-level visual motor control in a given visual scenario. However, that inhibited the overall evaluation of the current scenario of the agent. So they stitched the visual pictures together and make it a panoramic view. So that's their Now let's take a look under the hood of this work. So we will take a higher level understanding of the models. So as the name or the title suggests, the speaker follower model consists of two parts. Firstly, the follower model, which takes the instruction into account, and in return it gives the predicted routes. And the second one, the speaker model, it does just the opposite of that. It takes the routes into account and predicts the instruction in return. Both of these models are attention-based sequence-to-sequence models, which is very widely used in VQA and VLN at that time. Here you can see the basic diagram of a sequence-to-sequence model. As the name suggests, this sequence-to-sequence model takes a particular sequence into account and outputs another sequence. Now these sequences can be natural language instructions, or it can be a sequence of visual images. It can vary. So for follower models, it is the inputs are natural language and outputs are visual routes, which is the opposite for the sequence speaker models. And all these blocks, as you can see in blue and green, are based on attention, are basically attention blocks. Moving forward, now let's dive into the methodology part. In this step 1, the authors train the speaker model. To do so, they provided both the ground truth routes and the human instructions to the model, and after training, the speaker model can produce human instructions or predicted instructions based on the any visual routes. In step 2, the Fowler model is trained. To do so, we already have the trained speaker model. Now we can use the trained speaker model to generate some additional instruction and route pair using the finite dataset or finite routes that we have. So as a result, we have some generated data and already some annotated data in the dataset. So as a result, the dataset size increased, and using all this data, the Fowler model is trained. Now, in step 3 of this methodology, the authors propose their pragmatic inference part. This is nothing but a pre-processing techniques. In general VLN tasks, there is only the Fowler model, which takes the human instructions into account and provides a predicted route. However, as the authors have trained a speaker model, they use the already trained speaker model here as a post-processing agent. So as a result, the Fowler model generates not a single predicted route, but a few predicted routes, and those number of predicted routes are then passed through the speaker model, which in turns generate the corresponding human instructions, and comparing the predicted human instructions from the speaker model and the given input to the Fowler model, the final prediction is generated. Here, the utility of these post-processing techniques is that in a few cases where the Fowler model cannot determine a better choice between several predicted routes, then the speaker model here works as a tiebreaker. So that's how these post-processing techniques eventually benefits the model. Now let's take a look at the panoramic viewpoint, which is the last contribution of this work. So at that time, the existing works used what they call low-level visuomotor space, which is nothing but image by image action prediction. So a downside of this type of systems is that the agent at a given location needs to turn several times to get a situational awareness of its environment. So as you can see, the agent is at the same point, but it needs to turn 4 times to find the sofa, which is said in the instruction. But in this work, they stitched several images altogether into a panoramic viewpoint, which creates an ease for the agent to find the sofa, and based on that it can turn and take decision in a single go. Now let's take a look at some quantitative comparisons. Here you can see that the base Fowler model, along with the three techniques that is proposed by the authors, are shown with the success rate. So as you can see, with each technique implemented, the success rate increases both in seen environments and in unseen environments, which is of course a positive side, and the performance increase is very significant, as you can see here. Now let's take a look at the performance comparison of this work with the existing works. At first, the authors established the baseline with random directions, which is at 13% success rate. The success rate increased by the other two authors' works. However, compared to the works of Anderson and his team and Wang and his team, this work almost doubled the success rate performance, which was a significant one, and at that time this was the best performance quantitatively, and which is a very good improvement towards the human performance, which rests at 86% success rate. Now, I would like to talk about some research gaps in this work along with some of the existing works. Firstly, here the environment is considered a discrete one. However, in real world scenario, the environment is a continuous one. So the difference between that is that when such models will be used in real world scenario, the agents will not get a very discretized decision making systems. They will need to take decisions every milliseconds or update it every milliseconds. So that might create a problem. Secondly, in a known topology, the agents know the environment beforehand and can traverse through it or explore it efficiently. But in real world scenario, the environmental topology might not be known. Thirdly, here the agents are considered as Oracle Navigator, which can move through any object anywhere. However, the agent's shape and size should be taken into account because it cannot pass through any type of narrow ending if the shape doesn't permit it. And lastly, the perfect localization is a ideal case which is considered in this study. However, as I said, in real world settings, that might be a problem to achieve. So here are the references of this presentation. Thanks a lot for listening. Have a good day.